Good morning. Welcome to Cunning with CNG, Soliciting Secrets from S-Channel with Jake Kambic. You are, sorry, that was not the right line. So stop by the business line, the business hall located in Bayside AB. The Black Hat Arsenal is on the Palm Foyer on level 3, and there's also the Arsenal reception at 5 p.m. If you haven't picked up your merchandise today, it's your last chance to visit the Black Hat store and the bookstore as well. You can also visit the Kali Linux lab in Mandalay Bay A. And last thing we would ask you is to put your phone in silence or vibrate. And so without anything else, please give a warm welcome applause for our speaker today, Jake Kambic. Thank you.
All right, thanks guys. So really quickly, before we get going with the talk, we're just gonna launch an RDP session. And I will explain why in a minute. Okay, cool. So, you might be wondering why I did that. Well, today we're here to talk about S-Channel and Microsoft's implementation of TLS, right? RDP is one of the things that uses S-Channel, so by the end of this talk, what we're going to do is we're going to take that RDP session that I just captured, and we're going to be able to replay it even though it uses ephemeral key exchanges. So, let's get into how that happens. So what are you going to get out of today? Well, I just mentioned it. The big thing is we're going to be able to decrypt TLS sessions that use ephemeral key exchanges by analyzing Windows memory. The other cool thing that we're going to be able to do is we're going to be able to pull private keys and session ticket keys out of memory in Windows as well. So that's kind of neat. And then the other thing is, from a forensic perspective, we're going to be able to map public certificates and server name indicators, and we'll explain why that's kind of cool and important, to process IDs and login sessions. Logon session IDs. So how are we going to get there? Well, we're going to talk about SSL and TLS really quickly, just give you a refresher, and then we're going to go into what S-Channel and CNG actually are and how they work together, and then we're going to talk about the secret keys that we're going to be using to decrypt the data and what those look like and how many there are and where they are. And then the last thing we're going to do is talk about that forensic context and what's the value of that. And once we're done with all of those things, then we're going to go to that demo and we'll actually decrypt that session we just saw. So, really quick disclaimer, not an exploit. This is exactly how the spec is intended to work. Microsoft hasn't done anything especially wrong. Actually, for the most part, their documentation is fantastic and they follow the spec. One thing though, there's a few implementation specific oddities that we'll be talking about that maybe aren't the greatest. So also kind of goes without saying, but you know, if you're not using S-Channel, then this isn't going to affect you. So if you're not using Windows TLS library, if you're loading your own, ergo Firefox and Chrome, this doesn't impact those. And if you're doing something that's not TLS like TeamViewer, this isn't going to impact that either. So what is it going to impact? Well, it's going to impact things like Active Directory, Skype, Internet Explorer, Exchange, Link, all those kinds of things. And .NET applications and stuff like Citrix, so GoToMeeting for instance. So yeah. So background. I know that you've all seen the TLS Handshake like a gazillion times and you probably don't want to hear about it, but we're going to go through it really quick so we can talk about what actually gets stored in memory. So TLS, what's the purpose? Essentially two parties want to exchange sensitive information over an insecure channel. How do we do that? Well, client sends a hello and says, "Psst, server, I want to tell you a secret." And he opens up his little trench coat full of Cipher suites and full of TLS extensions. The server gets that and it's like, okay. If he likes what he sees, he says, take this number, which is going to be a session ID or a session ticket, depending, and the session ticket comes later. And he's going to say, here's the extensions we're going to use, and here's the Cipher suite we're actually going to use. And then everything else that happens after that is going to be dependent upon those decisions. So the kind of certificate that we pass and whether or not there's going to be a server key exchange all are dependent on this Cipher suite. So what does a Cipher suite look like? It looks like that thing at the bottom there. specifies the protocol version, TLS, right? Specifies the key exchange, so ECDHE is an example, and then the signing mechanism, the symmetric key mechanism, and then the MAC mechanism. So, so once he sends that over, we're going to talk about, in this slide, just RSA, and then we'll move on to talk about DHE and stuff like that. So once he sends it over, he says, here's my certificate, which is my proof of identity, my signing cert, and also you're going to use this then to, that public key inside of that certificate to encrypt a bunch of random data that the client generates and send that over. That random data is the pre-master key, so that's the client key exchange. Every key exchange is going to have a client key exchange, but again, specifically in RSA, what we're doing is we're generating random data, shipping that over. Now in theory, at this point, we both have a shared secret on either side of the connection. But because the key exchanges are different, the pre-master secret is always going to look a little bit different. So instead, we do some special magic stuff, and we get a fixed length master secret on each side that looks the same every time, so that we can then mix in some public values and then mint ourselves some session keys. Once we've minted the session keys, then we basically say 1, 2, 3 switch, which is the Cipher, change Cipher spec message, and then we start using our symmetric Cipher, which is almost always going to be AES. Cool. So why does that matter? Well, the pre-master key, the master key, and AES keys are going to exist on both sides of the connection. That's the big takeaway. And there's going to be these other secrets that are going to depend on the type of key exchange we use. So that's all cool and well, but one problem is like it takes a long time, and obviously we don't have to do that every single time. So wouldn't it be nice if, since we've already exchanged this shared secret, if we could just keep it for like just a little while, and then next time we wanted to talk, the same client and server want to talk, if we stored that session ID or ticket, we could then just reinitiate that connection, because we now have a unique identifier for the previous connection, and we have those things in memory. And sure enough, the guys that wrote SSL and TLS thought of that and thought that that was a good idea. It's called session resumption. So that handshake is basically, hey, okay, let's switch. The client sends the identifier for the connection to the server, so the server knows who the heck we're talking about. And then they reference that in memory and look up their shared secret that they've stored. Or if you're using session tickets, the client sends the session ticket over, the server then decrypts that and checks that shared secret, and they start their communication again. They mint those session keys and then start that communication. So that's all cool and well. You might have noticed that there's like a few potential problems with that. First of all, talking about RSA, again, everybody we've known for a long time, like 20 years, that there's a problem with RSA, which is we're shipping that private material over the network, right? And then that private key that was used to decrypt that private material on the server side gets stored on disk. So big problem. Well, we can now essentially, after capturing that traffic, grab that private key, decrypt it, decrypt the session after the fact. So Diffie, in his paper in 1992, Diffie basically said, Whitfield Diffie, hey, you shouldn't do that. We should do this thing called the Diffie-Hellman key exchange instead. And there's this concept of perfect forward secrecy, and that violates perfect forward secrecy, because anything that you and I have done, if we've actually been able to establish a secure connection together and exchange that secret, at no point in the future should that then be compromisable. We've done it securely now, it should stay secure. Cool. So how do we do that? Well, we don't send secrets over the network, right? Diffie-Hellman actually uses the communicative powers of exponents to do some cool magic stuff and just send public values. And on top of that, we really shouldn't be using a key that's stored persistently on disk for the encryption part. We should use that for identity and signing, but we should definitely do something a little more ephemeral. So the idea is we're going to, for perfect forward secrecy, hopefully we would just use a key once, throw it away, and then use another one for a different session. The reality is that's not what actually happens. So what does TLS actually do? Well, we've been talking about sort of like the private keys, but obviously caching that master key is just as bad, especially when the spec says you can cache it for, well, session IDs for up to 24 hours. In theory, a master key could outlive that if we just change the session ID and keep using that shared secret. That's not what actually happens in Windows, and we'll talk about that luckily, but there are some implementations that even store this on disk, so that's not good. What else does TLS do that's potentially bad? Well, the session tickets themselves are basically the same problem with RSA, right? We're encrypting the state, so the master key, we're shipping it to the client so we don't have to think about it, and then when the client wants to talk to us, he ships it back, we decrypt it, verify that it's actually what we thought it was, and we start that connection again. So that's really cool, because then the server doesn't have to worry about storing it, and you can do this, if you share that session ticket key in the background, multiple servers can actually resume each other's sessions, but the bad thing is we're now sending that over the network again, so we're sending secrets. And then on top of that, we have the implementation specific oddities that are bad. And one thing that we're going to talk about today is things like, I don't know, storing symmetric key schedules. So the key itself is random, but the key schedule is not, and that creates problems. So, and the other thing is like, okay, yeah, it would be nice if we use this ephemeral key once and then we just got rid of it and grabbed a new one, but that's not really performant. So maybe we could just reuse the ephemeral key for a while since it's in memory, and that's good enough. That's mostly perfect forward secret, right? Well, I guess we're going to find out. So, Schannel and CNG. Name of the talk, how do these things come into play? Again, secure channels, Microsoft's TLS library. It's technically a security support provider. That doesn't really mean anything. It's a library that gets loaded into the client process and this magical thing called the key isolation process. So basically, Microsoft doesn't trust your little C# web server to be touching private keys. So instead, it's going to house everything in this key isolation process. And if you've ever done anything with Windows security, you know that the process that houses all the secrets is LSAS. So that's where it's going to be storing those. Well, how does CryptoAPI next generation get in play? Well, it's as we all know, the next generation is always the best generation, but it was introduced in Vista, so there was one good thing that came out of Vista. And basically what it does is add support for AES and ECC. So Schannel handles the TLS stuff, and then all the actual cryptographic stuff gets handled in Decrypt and Encrypt and these other libraries that are part of CNG. So what does CNG do? It basically does two very distinct functions. It stores things, and then it encrypts and decrypts things. So encrypting and decrypting is done via the data protection API, which actually Ellie Burstein, who spoke earlier, like yesterday, was the guy who did the seminal research on that. So we'll talk about that a little bit. And then it stores them with the key storage providers. So does Schannel actually use this perfect forward secrecy thing that we spent some time talking about? Well, it turns out, yeah. So I took samples based on, again, CNG instances of Windows that use it. So looking at Vista, we still preferred RSA keys because, well, we've just introduced this new ECC thing. We don't really want to potentially break that key exchange along with everything else. So we still preferred RSA, but we supported ephemeral suites, and we supported elliptic curve suites. And then starting with 7 and moving forward, we actually embrace those, and that's pretty much exclusively what we want to use. So the code to actually list what your Cipher suite preferences are is available from Microsoft. There's a link at the bottom. And then starting with Windows 10, we actually have a PowerShell commandlet that'll do that for you, so you don't have to worry about that. So takeaway, AES is going to be the symmetric cipher we prefer, like by and large, and we now prefer ephemeral suites with Schannel. So using that whole RSA key off disk thing to decrypt sessions is no longer really viable. What else do the docs say? Well, okay, we can't use the RSA key, but Microsoft does implement that whole caching thing we talked about with TLS for session resumption. And they store the master key, the Cipher suite, and the certificates. That's kind of neat, right? So the other thing that they tell us is specifically that LSAS will consume more memory when you enable that cached life to live longer, or when you enlarge the size of the maximum cache size. By default, we're storing 20,000 cache items. That's a lot. Maybe not a lot for a web server, but a lot for a client, right? So yeah, so now we know we're targeting LSAS. We know that we're looking for at encrypt specifically because the docs mention that encrypt is a secret agreement router. We'll take a look at that. And we're looking at TLS sessions that use ephemeral suites. So this is Microsoft's, this is a prettified version of one of the Microsoft diagrams. It looks complicated. It's not. Basically what it says is whenever a client wants to, what I told you earlier basically, whenever a client wants to do a key exchange that calls into LSAS, LSAS actually does the key exchange on both sides, the server and the client if they're Windows. And then LSAS passes back a security context and a credential handle to the symmetric keys so that the process itself, the client process, can handle that tunnel, because it would be terribly inefficient for LSAS to be grabbing application data and shipping it back up to that client. So what does that mean for us? That means that the session keys are going to be stored in the client process. Everything else is going to stay in LSAS. Cool. Well, what does it look like when it's stored in LSAS? This is another Microsoft diagram that I prettified. It's CNG. So more or less, it trickles down. There's these things called key storage providers, and then there's blobs that are going to get stored. And the way that they get stored and how that happens is going to depend on what kind of secret it is. So if it's a RSA secret or if it's a elliptic curve key, for instance. All right, cool. So in summary for the background, we're going to look at LSAS, we're looking for keys, and we're doing that because that's where the handshake happens and because Schannel prefers ephemeral cipher suites. Excellent. Why do we want to do this? Well, basically we want to be able to try and, we want to try and subvert perfect forward secrecy and how it's implemented, because that would be really cool. We can then decrypt sessions after the fact. Even if we can't do that, we definitely want to be able to learn more about the sessions for forensic purposes. Again, being able to map it back to who said what to whom, looking for public keys, especially in cases of like if there's any malware that's using S-channel for some reason. And then if we are an adversary, it would be really neat if we could grab those things out of the cache and then decrypt sessions that happen in the future, right? Because we've cached those and there's a time value on that. And anytime we make a new connection, we're just going to go back and look at that cache item. So that would be really cool. Or maybe be able to pull out the private key, and if we can do that, we can then, like the persistent private key, the signing key, if we can do that, we can then impersonate the server itself, which would also be kind of awesome. It'd be great if we could do that without touching disk. So secrets, right? What do these secrets look like? Well, here's all the kinds of secrets we've talked about so far that could exist in a given connection. So you got session keys, you got the master key, the pre-master key, and those are both on the client and the server. And then you have the ephemeral private key, the persistent signing key, and the session ticket key that could exist, and those would be on the server only. So what do they actually get us? Well, the session keys are only going to get you a single connection within the long scope because they don't get cached, right? They get regenerated, and based on you pull in the client random, you mix it together, you stamp out whatever your keys are going to be, your session keys are going to be from the master key. So they're only get you a single connection. The master key and the pre-master key, in theory, will get you the whole session. So that means if we make multiple connections back and forth and we're reusing that master key, if you've got it, you can decrypt all of those. Cool. What about the ephemeral key and the session ticket key? If we can grab those, now we're cross sessions, right? So if we reuse that across multiple sessions, then we can decrypt all of those as well. And then the private key, the persistent private key, gets us identity, and if we're using RSA, it also gets us the same things that the ephemeral private key gets us. So obviously we're focusing on trying to get the master key. That's what we're hoping for. We know that gets cached. It'd be cool if we could get the other things, but what do we actually get? Well, we got them all. We can pull everything, all of those out of LSASS essentially. The top one, the session keys, obviously they're purple. That's stored in the client process. Anytime that you see a green symbol, that means that they're stored unencrypted in memory. And then I know you're all looking at that one yellow symbol that's different. You're like, hey, what about that? Well, that's the private key is stored encrypted in memory, but don't worry about it. We'll talk about it. You can actually just decrypt that straight out of memory, so no big deal. The one other thing that you see is not on there, or it's kind of in the corner hidden away, is the pre-master secret. We don't need it. We'll explain that in a minute too. So how do we do this? How do we get to the point where we can actually pull all these things out? And the other thing is those paths, you're going to have access to these slides obviously later, but those paths are data structures and offsets into those data structures based on symbol names and my own naming conventions, and I'll explain that in a minute too. So how do we get there? Well, I decided to start with session keys because they're closest to the data itself. They're the most ephemeral. You're probably not going to encrypt something that needs to be used for active encryption. So the keys are going to sit in memory unencrypted. I started with AES because, well, that's the preferred cipher for like everything, for the symmetric cipher. So AES keys themselves are random, right? They're small for the most part compared to memory, and they're very random. So you shouldn't be able to detect them. So how do we detect them? Well, the guys over at Princeton published a cold boot paper a while ago where they talk about the fact that a lot of times implementations calculate this key schedule because AES keys get expanded into round keys basically, and they get stored as a schedule. And they talked about how, again, for performance, we're storing those a lot of times. Well, Microsoft's no exception. We do, in fact, store those. So what I did was I just took a tool. I didn't want to write my own. So I took one from Jesse Kornblum. I scanned the client process and the server process, and what you see there are matching keys in both. So you might be wondering, why are there 4 matching keys? I thought we got an AES key. Well, there's a server key and a server write key and a client write key, right? And on top of that, there's also MAC keys. But I think that I had 2 connections there. So yeah. So at this point, we've got the session keys. This is what they look like in memory. So what you're going to see for the rest of the talk is you're going to see a lot of WinDebug. And the reason I did that is I gave the full command that I ran at the bottom so that you could basically do this. If you want, you can follow along if you've got WinDebug run on your machine. And then I've got the structures next to it that map to it. So this is how this works. So session keys, we're not going to spend a lot of time on them. They're not really that great for us because connection specific. We want at least session specific so we can to make something useful. The basic structure is there's a length, there's a magic value, and then there's the protocol version, and again the Cipher suite version, and then there's a flag for whether or not it's a write key and a pointer to a decrypt key. So again, decrypt, part of CNG, handles all the symmetric cipher, handles all the cryptographic primitives. And you might recognize that because Benjamin Delphi, who wrote Mimikatz, did a lot of work with decrypt keys and things like that because AES and 3DES are used in encrypting other kinds of secrets. So if you go look at the code for Mimikatz, you'll see what he calls those. He calls the MS symmetric key, I think he calls that a bcrypt key and the other thing a bcrypt key handle. The reason I call it an MS symmetric key is because of the symbols that Microsoft uses and the fact that the magic value for it is MSSK, Microsoft symmetric key, and it's always a symmetric key. So there you go. So we've got those, but we're not going to spend a lot of time on that because the really cool thing that got us was this magic value, 3LSS, which is actually SSL3. It's stored little endian. So SSL3 kind of indicative that we're talking about SSL. But I thought maybe it was referring to the protocol version. And then I started looking at it and scanning the modules to figure out where those were stored in memory and in what sort of functions they were used. And I found quickly that, in fact, there's a SSL 1, 2, 3, 4, 5, 6, and 7. And so they're not actually referring to the protocol version at all. They're referring to the type of secret. And they all exist inside of this Encrypt SSL Provider, DLL. And it has a series of validation functions that were incredibly helpful. And they're very simple. All they do is they take a pointer, they check a length value, they check a magic value, and then they return that pointer. So the really cool thing about that is now that when we run through those and if we have validation functions for all those, they're named very appropriately. So we can tell what those actually are. So what does that mean? That means that we know now that SSL5 is the master key structure. We know SSL4 is the key pair structure, which is going to be the private key. We know that SSL6 is the ephemeral key. And there's two of them that didn't really have validation functions. That's no big deal. SSL3 we already talked about. That gets used in things like generate TLS session keys and to encrypt and decrypt. And again, it's storing an AES key and it gets passed into the client. We found matching things. We know that that is the session key. So the other thing is this SSL7. Okay, what's that? Well, that's this pre-master secret that I told you we were going to talk about. The pre-master secret, it's not really functionally useful. It doesn't do anything the master secret doesn't do. And even though it always exists for every type of connection, this specific structure only stores the RSA pre-master secret and it gets destroyed. It's too beautiful to live. It gets killed really quickly. You're never going to see it in memory unless you capture it right at that moment where the session is taking place. So not really useful. The master secret. So this is the Goldilocks secret. This is the whole thing where we get multiple connections for a session, and we know that Windows caches this, and this is what it looks like, basically. The great thing about it is incredibly simple. It actually stores the master secret directly inside of that structure. So because of that, we could really just scan for this SSL5 magic value, pull all the master secrets out, and then brute force the session for a given session ID that we're interested in just to see if we can decrypt it with what we've got. That obviously isn't very elegant, but in the case that the cache item has already been decommissioned or purged or what have you, if there's still an SSL master key, that's an option for you. But what we really want is a unique ID. So what does that look like in memory? That looks like this, that same structure I just showed you there, but then parsed out with WinDebug. And then you can see that there's a pointer also to the Cipher Suite version because we need to know if we're resuming how we're going to take that master key and then mint those into session keys. So yeah, so then what do? Well, we take that and we map it back to a cache item. So I was able to figure out exactly what a cache item looks like, what are the elements inside of a cache item, and it stores the unique identifier, so either a session ID or a pointer to a session ticket, and then that also goes and through similar to how bcrypt works, there's an encrypt SSL key handle that then points to this master key. So at this point, we now have session cache item, ergo unique value, mapped to the master key. So we can now pull that out and then we can decrypt sessions directly. Houston, we have plain text basically. So what does that look like? Well, the easiest way to do this is just to dump this into a format that Wireshark understands, and then you can just load that straight into Wireshark. So at this point, yeah, we've got everything we need. But why stop there? There's other interesting things to grab. So the ephemeral and private and persistent private keys, right? The private certificate and the ephemeral key, we saw that those were SSL4 and SSL6. Well, they have the same structure, which makes a lot of sense. They're both private keys. They get stored in this with this key storage provider. So what happens is we have a SSL key pair sort of struct. At the very bottom of that, there's this what I call a KPS key storage provider key pointer, KPSK pointer. That points to an encrypt key handle, which then points to that KPSK structure. Inside of the KPSK structure, We then have a pointer, depending on if it's ephemeral key, we have a pointer off to this MSKY structure, which gets used to store the ephemeral key, or it points off to a DPAPI blob, which is the private key. And we'll go through those directly. So this is what the ephemeral key looks like, stored in memory. The one thing that tripped me up was that it was stored little endian, and nothing else is stored little endian, and the byte arrays and everything else. So it was just, wasn't expecting it. But Microsoft actually has functions specifically to flip it from a little endian byte array to a scalar so they can use it in their calculations. So what I've dumped here is there's this S-channel, as you might have seen from the symbols, and I didn't mention it explicitly, but it's object oriented, right? So there's classes. So what we have at the bottom of that WinDebug thing is I'm looking for a VF table of a class, essentially the C ephemeral key data, and that points to the public key, and then points all the way down to this through that SSL 6 all the way down to this private key, this ephemeral private key. So what can we do with this? Well, in theory, we could actually pull this out, run it through something like SSL, throw it into a PEM format, and then decrypt sessions with it. Wireshark doesn't currently support that. That's something that I actually am going to add as soon as we're done. It's just they haven't had a need so far because nobody's pulling ephemeral keys out of memory. So, but yeah, now at that point you can decrypt multiple sessions because this gets used across sessions. So that's kind of cool. Yeah, so also what you have here, the KPS key structure also stores the NIST curve and the curve parameters so that you can generate the public key, which is how I verified that this was in fact the private key, because otherwise it looks like, again, just sort of random data. That MSKY structure that this is stored in, by the way, gets used elsewhere, and I'll talk about that when we get to it. But yeah, so at this point we've got the ephemeral key, we've got the master key, we've got the session key, we've got the pre-master key, really, kind of, we don't really need it. And what about that persistent private key? Can we get that out of memory? That was encrypted, that was a little yellow lock. Well, yeah, we can get that, of course we can. It's stored with DPAPI, and it's stored in memory. Now, if we wanted, we could grab the DPAPI master key off of disk, and that red there that's on the WinDebug screen, that's the key GUID for the DPAPI key. So we could actually go find that, decrypt it, and then have it that way. But we don't really want to go to disk. I mean, that's a lot of work. And what if we don't have that? What if we've only got the LSAS process dump itself? Well, that's no problem because the DPAPI key itself gets cached. The master key gets cached in LSAS as well. And Benjamin Delphi did a lot of work on this. I actually went through and tried to reverse it myself, or did reverse it myself, and then saw that he had done it and felt stupid for not checking his code earlier because he's kind of the man when it comes to LSAS. But anyway, so what I'm showing you in this WinDebug example is I basically looked at that key GUID, and then I scanned the master key cache because I know what that structure is. I dumped out this single entry that maps to that key GUID. So that's the encrypted DPAPI master key, and then directly above that are the initialization vector and the 3des key that are used to unencrypt that. Once you have this DPAPI master key, you can then use that on the DPAPI blob itself to decrypt the private key, and you wind up with something like this. So on the lock side, we have the key from disk, and the DPAPI blob is highlighted in gold, and then we have what I pulled out of memory and decrypted, which is the RSA. And you'll know that it's actually the private key when you've decrypted it properly because it says if it's an RSA key, Microsoft stores it with RSA2. So you can see that. So at this point, we've pulled the private key directly out of memory. We didn't have to touch disk to do that, and we decrypted it. So that's kind of cool. So the last thing that we have to talk about as far as secrets go before we get to the forensic stuff is this concept of session tickets. And so far, Microsoft has actually been doing everything by and large correctly. I mean, the reality is those things are supposed to be short-lived. They're in memory, so you really can't fault them for storing them unencrypted. And they do encrypt they keep the public or the private key, the persistent private key, encrypted in memory until they use it. So props to them. Granted, they store the other things so we can decrypt it all out of memory, but still. But session tickets is kind of where things get a little bit fuzzy, and their documentation starts to get really bad. So session tickets were introduced with Server 2012, and we have these PowerShell modules that will enable a administrator managed session ticket, but they don't ever really tell you, okay, this is how you actually go about enabling them. What you find is in the Windows 8.1 preview release notes, they're like, BTW definitely need to be disabling session tickets by setting this specific registry value to 2, because if you don't, stuff's going to break. So when you look at that, I said, okay, well, 2 is disabled, 1 is probably enabled, it was enabled. So if you go through the steps and you actually set up session tickets by creating a new session ticket, basically everything I've done in this PowerShell window right here, you create a new session ticket, you enable a session ticket for the specific user, and then you enable this setting that in the registry to actually enable session tickets, then you can actually start using them. So there's also this cool nifty little function called export TLS session ticket key, and what you might notice is that there's a key path. So when I'm creating these keys, I'm actually creating these session ticket keys on disk. This isn't in memory. And then I'm enabling them for a user, and those are getting stored on disk. So what does that mean? Well, this is what the key file actually looks like on disk. So you've got the DPAPI blob at the bottom, you have the key GUID, and then the size of the DPAPI blob directly above that. And then there's a value that I didn't take the time to figure out what it was because I didn't need it. But it's probably a macro assault or something. So what about just doing this straight from memory? I don't want to have to grab this key from disk. It's kind of scary that it gets stored on disk. What does that mean? Well, luckily, it does get loaded directly into memory. There's a key derivation function that happens. I decrypted this with DPAPI pick off from disk, looked at it, looked for that value in memory when I ran through, matched them up and said, okay, here's where it's getting used, and then followed the chain and saw that it actually gets passed to a key derivation function. Then we get our magical AES key that we want. Very cool. Once you have that AES key, it's straight AES to decrypt the session tickets. So, and interesting thing, there's no random value that gets passed in with that key. So having the key from disk, basically you can then regen, it seems, and across reboots that AES key gets loaded, that same AES key gets generated, so you can actually take that, pass it through the decrypt key derivation function, and then after you stole that, you basically have the same thing as an RSA private key for anything that uses session tickets. So there's that. So what does the session ticket itself look like? Microsoft actually followed the spec and improved upon it. They use a key, they put the key GUID first, they put the IV just like the spec says, and then they take the MAC and instead of storing it after the encrypted state, they store it before, so that if they want to change the length of the encrypted state at any point in the future, they don't actually have to go through and change how they parse everything. So props for that. That's cool. They're using AES 256 instead of AES 128, which is what the RFC originally proposed. And we're going to talk about what gets stored inside of it once we show you quickly how you decrypt it, which is literally just AES. So the MS Key Protect stores this key, this session ticket key, and in a cache directly inside of the module memory, actually. And all you need to, there's no symbols for the cache, but all you need to do to find it is have the key ticket GUID, which gets sent with the session ticket itself. So if you know what session ticket you want to decrypt, you can just grab that, you can then search memory, extract that AES key, or you could just extract it because it's the only bcrypt key that's really getting pointed to inside of the MS Key Protect structure. And we now know what the magic values for the bcrypt keys look like. And then you can decrypt these offline. And so a decrypted session ticket basically just has that SSL5 structure, the master key structure, a timestamp, the protocol information and stuff like that inside of it. So that's what this looks like. The first window is the Wireshark with the session ticket. Then you have, I dumped out the session key entry and then the session key, and then I have the decrypted version that I just, for visual purposes, just passed to some online thing that does AES so you can see it decrypted. So now, at this point, we have basically decrypted, we've extracted and decrypted every kind of key that you can possibly have for a TLS session out of Windows memory. So that's really cool and all, but you might be wondering, like, well, what if I don't have a PCAP, or what if I don't care about decrypting future sessions because I'm not a bad guy, right? I'm just a forensic guy. I want to know how I can use this for my own purposes. Well, there's a lot of context information that gets stored inside of those cache items. So what kind of metadata do we have typically for TLS? Well, we have this idea of the server name indicator, and this is something that kind of builds on top of the functionality you get out of volatility and out of recall with their con scan, right? So if you do a connection scan and you see that, hey, this process reached out to this IP address on 443, that's all you get. But the reality is that there can be many virtual servers at that IP address. So one of the cool things that TLS does is when it sends a request out, it stores this, S-channel stores the server name indicator that says, here, by the way, is the specific guy that I want to talk to at that IP address. And we store the public cert, so we can use that as well. The other thing is obviously you can use the key GUID, and potentially ALPN can kind of tell you what protocol was going to come next, those kinds of things. Core functionality from TLS, the random values typically start with a timestamp. So that's kind of useful if they follow the spec. Not everybody does. And then you can actually fingerprint based on the session ID, which is something that somebody discussed in the dual EC paper. This is not supposed to happen because in theory, a session ID is supposed to be random, right? Well, no, it's supposed to be arbitrary. And Microsoft actually has S-Channel specifically has a fingerprint because it takes, according to this dual EC paper, it takes that 20,000 value that we saw earlier, and it performs an operation on that with the first D word of the session ID. And so what you wind up with is 2 bytes of random data, 2 bytes of zeros, and then the rest is random. And it becomes a very obvious pattern to pick out if you're looking at a bunch of TLS sessions. You can easily see, yep, that's S-Channel. So the other thing is we saw that there's variations in the Cipher suites that are preferred based on the version of Windows. So in theory, those get stored temporarily as well as part of that security context. You could actually sort of start to figure out what kind of server they were talking to. Was it a Windows, Server 2012? Was it Windows Server 2003, and stuff like that? So you can kind of find out some cool information just by looking at some of that ancillary data from a forensic perspective. So how long does all of this actually get cached? We've been talking about this for a while. We've talked about the keys. We talked about this cache, and we can extract stuff. Well, by default, everything gets cached for 10 hours. So not the 24 hours that we were hoping for, but 10 hours is really pretty good, especially for something like RDP that we did earlier. So I haven't stopped that VM. It's still running. I'm not going to sit here and wait 10 hours with you until I actually pull that out. We'll do it quickly at the end. But yeah, so that's kind of neat from an incident response perspective. These things sit in memory for quite a long time. Also, we store 20,000 entries, and we separate those entries into server cache items and client cache items. So one kind of cool thing that you can ask yourself is, like, when is a client a server? Well, RDP is a case where the client acts as a server, but when else should there be server entries in there for the client? Maybe there shouldn't. So it can kind of help you figure out things about whether or not a host has been compromised and stuff like that. So the other thing is, by default, when a session gets purged, there's a cleanup function that runs about every 300 seconds. So you might have a window there, potentially, depending on when that was last purged, or when that last ran, to actually extract them after they've been decommissioned. And so the only thing the big caveat to this is S-Channel is a library, so the process has control. If the process wants to purge its own session cache, it has full right to do so. It says, hey, LSAS, get rid of that, I'm done with it, and LSAS will comply. So so they can do that. One example is, like, IIS supposedly rotates the ephemeral key every 2 hours. Now, 2 hours to decrypt every session that was made in that time period, still pretty darn good, but at the same time, that's something to be aware of. And the other thing is, when a process terminates, and this is the really sad part, S-Channel clears the cache. So because it's centralized and it's maintaining control of all of that, for all the different processes, it actually stores the process ID, which is good. Right, so inside the session cache, we have a process ID, but when that process dies, S-Channel just purges those. So the good thing is things like RDP run as services, so you don't have to worry about that. Again, most of the things where you're going to have a server case, it's going to run as a service itself, so you won't have to worry about that. But yeah. So what does your S-Channel cache actually look like? Well, here's an example of a 64-bit S-Channel cache, and it's a volatility V-type. So the very first thing is that VF table. So if you go back and you look at the WinDebug stuff, you're like, why does it keep looking for these VF table symbols? Well, if you're not really terribly familiar with how Microsoft C++ compiler works, basically when you have a class, the very first thing that gets stored is a virtual function table if you've got one. And so you can actually use that as a heuristic. It's not a magic value, and it'll change with every time that the binary gets recompiled. But you can actually use that to then decrypt, or you can use that, to find the classes. So that's really kind of neat. So first thing gets stored is VF table. Second thing is that pointer to that master key. And then some things to call out are that logon session UID. So every time you log on to Windows, there's a unique identifier that gets generated. This isn't your user ID. And that gets stored here as well. So you now can map back the session ID, the logon session ID, and the process ID to the specific TLS session, which also has public certificates and things like that. So that's really kind of neat. The server cache, much smaller. And again, you can see the rough sizes of these. I haven't actually gone through and grabbed every field. I've grabbed as many as I could in the time period I had. And so that's what that looks like, and that's that parsed out as well. And then Vista, because, everybody loves Vista. But Vista's kind of proto S-Channel. It's before we really did it's before we really did classes. So it's more of just a list entry structure. The very first thing is a list entry, and then you can loop through and find all the other cache items that way. So automating it. So that's all cool and well, but I don't really want to go through and be messing around with WinDbg all the time. How did you make this useful to me? Well, there's a volatility and a recall plugin, and we'll demonstrate that. And the default behavior is just, we're just going to dump out session IDs mapped to the master keys in that Wireshark format. So you can literally, and this was really done because there's some non-technical people I know that would find this useful. So this is done so that you can literally just take that, throw it into Wireshark, and then decrypt that traffic. So cool. Eventually, I'd like to do it live. I'd like to create a PowerShell module, and I'd like to create a or incorporate this into Mimikatz, because I think, again, this is all LSASS. This is Benjamin Delphi's area, so I think that if he's amenable, we can maybe do something like that. So limitations. So we're working with internal and undocumented structures. There's I think it was FireEye put out a blog post in early, maybe like March of this year, and they said, hey, by the way, there's this downgrade thing that happens sometimes with session tickets in an S channel. And so it seems that about after that, there was an item that was inserted into the cache. So not a big deal, but it changes those offsets that we saw, right? So the problem is, well, if you have unpatched system and patched systems, then you have to do a little extra work if you want to figure out, how to get to those. But it doesn't affect it's inserted after the session ID, so it really only affects session tickets and things like that. But anyway, the things to be aware of when you're working with internal and undocumented structures is there'll be some limitations like that. We're also talking about using symbols, right? So because we're using symbols, Microsoft can take them away. They can say, well, next time we recompile that, you're not going to have those. But we can still do things without symbols, and in fact, we do that without symbols in volatility, for instance, and it's actually it's not that hard. And then the other thing is you need to be able to read LSASS, right? So not a problem in 2016. I mean, you've seen, again, Mimikatz is ubiquitous, used everywhere. But if you can read LSASS memory, that basically means you own the system, which basically means that you can do a lot of other really bad things, and maybe this isn't as big of a deal, except for obviously the session ticket key and the private key, because then you can impersonate and decrypt after the fact. But if you own the system, you own the system. So that's why it's probably most useful in a forensic context. So let's go back to that just quickly, and I hope this works. So I created that session earlier, that RDP session, and we can take a look at that. Yeah. So let's look at the server hello really quick and just make sure that this is ephemeral. You're going to notice that that's TLS 1, not TLS 1.2, and you're going to say, he's cheating. Well, RDP replay, which was released for just recently, open sourced, I had to modify that, and I didn't have time to make it support TLS 1 and 1.1 and 1.2. So it's still using an ephemeral key exchange, which is the important part, and we can see that right here, ECDHE. So let's minimize that. So we're going to simulate acquiring RAM from that virtual machine, the Windows 10 one that I remoted into. And this is going to take a moment because we're dumping 4 gigs of memory, so just bear with me. And then, so you saw the screenshot of the volatility plugin. That works. I want to show you the recall thing, so you know that I have both of them. They both work. So I'm going to go ahead and do that for you really quick. Nothing up my sleeve kind of stuff. It's going to be angry because it can't talk to the internet. And then it's going to dump that out for us. That'll probably take a moment. In fact, if anybody has questions, I don't know how we're doing for time, but you can probably queue on those. 10 minutes? Okay, perfect. Okay, so there's the so that's the session ID and the master key dumped out. So I could actually, we'll just do this. So dump that into this file. And then we're going to read that PCAP file in, and we're going to read this. I think that's where I stored it, was demo.txt. Okay, cool. And again, this is a modified version of RDP replay that'll actually take the Wireshark format. And voila, we are now replaying an RDP session that used ephemeral Cipher suites. So, ta-da. Thank you. You'll see the things I typed with the dates earlier, just to kind of give you a rough idea that I'm not cheating you. And then, so if there's questions and things like that, please come up to the mic and ask me anything you want. And also really quickly, so that's the end. You can ask me questions at you can contact me on Twitter as well if you want to ask me questions now. So at @tinrabbit, and then I just really want to say a special thanks to Anya Doyle, who's just awesome, and to Dr. John Ross Wal Robinstein, and Marcus Rogers of the Purdue Cyber Forensics Laboratory, and Michael Haley of Volatility, who I don't know if he was able to make it today, but he was really, really nice and looked over my stuff and just generally awesome. So, and don't let me forget Tatiana Ringenberg. So, yeah. So that's it. Thanks very much. Question?
Okay, so have you contributed the RDP replay modifications you made upstream, or is that modified version available anywhere? 'Cause that's pretty sweet. Just aside from all this.
Yeah. No, so I haven't yet. I am gonna. I'd actually like to completely rewrite it, but I'll make what I have now available. It's just that it's compiled with an older version of X-Free RDP. So, but yeah, the guys at Contextus are awesome for open sourcing that, and it's really cool. So I definitely will contribute to that.
Yeah, because this whole thing is really awesome because I've wanted exactly this for a very long time.
Yeah, me too.
But as kind of a usability thing, do you have any solution to the problem of like if you have the NSS keylog format and you stick it into Wireshark and decrypt the things, you then have to, like, every time you have a different stream, I'm sure you ran into this all the time, you've got to go through the thing and change it because there's no way to like pair them together in a way that like you now have a decrypted PCAP that like exists in perpetuity. Do you have like any solution to that? Because I've looked around for a long time and I have no idea how to fix that.
Yeah, so again, what I'm hoping to do is I'm hoping to go back and look at the SSL utils dissector for Wireshark and kind of change that, because there's a lot of things like, for instance, the pre-master key, once you have that, the process of turning that into the master key, it doesn't matter how long the pre-master key is or what it looks like, is the same. So really, at that point, there should be a unified interface to be able to do exactly what you're talking about through Wireshark. Where once you can...
You mean outside of the keylog format?
Yeah, that's what I'm saying. So my point is that you should be able to take the keylog format, you should be able to take a private key, you should be able to take a ephemeral private key, and no matter what, once you get to that point, it's all the same.
Yeah.
So
I mean, you can do the encrypted pre-master secret and a few other things the decrypted pre-master secret and like the session ID. It's a weird collect, but I agree that they only take like 4 formats there, and then.
But again, like it's Wireshark, it's awesome. So I'm not saying
it's pretty sweet. I just wish that you could save the PCAP after you decrypt it.
Yeah,
thanks.
Yeah, no problem. Anything else? All right. Well, cool. Thanks very much again.